Okay, today we shall start moving towards chapter 3. We won't read chapter 3 today, but let us start preparing for chapter 3. The first thing we are going to do is give another equivalent definition of perfect secrecy, which we will be using in chapter 3. Okay, and that is called the adversarial indistinguishability experiment. The adversarial indistinguishability indistinguishability experiment. That's a mouthful. Took me a couple times to practice it before, and I still struggled with it. Okay, so what is the adversarial indistinguishability experiment? Well, the adversarial indistinguishability experiment says that suppose there is an adversary A, okay? Adversary fancy A, okay? And they get two messages, okay? They specify two messages. Messages M0, M1, okay? From their entire message space, they get to choose these two messages, and they are encrypted by some random key, and the resulting ciphertext is given back to him. Message encrypted. One of the messages chosen uniformly, that is to say with half probability for each, encrypted and encrypted using a random key, and resulting ciphertext is given to A, and resulting ciphertext given to A. Okay, in that case, A guesses if the ciphertext is encryption ciphertext C is encryption K of M0 or encryption CK of M1. Okay? And the idea is experiment succeeds, A succeeds, A succeeds, C succeeds if he can guess, if guess is correct. Guess is correct. Okay? And then our, an encryption scheme is perfectly secret. Encryption scheme is perfectly secret. If no method or no adversary can succeed with probability better than 1/2. Can SUCCEED with probability greater than 1/2. Okay, the probability 1/2 is trivial. Getting probability 1/2 is trivial. You just say always that I am going to guess whatever happens, I'm going to guess M0. And since it is uniformly, if the message is chosen uniformly, half the time the message is going to be M0, half the time is message is going to be M1. And so it is always, you're going to get half trivially. Okay? Note, we are not putting any limitations on the computational power of alpha. No limitations on computational powers of A. Okay? So this is an important thing because this is what we are going to be talking about in the next chapter. Okay? So in terms of systematically writing down what the experiment is, the experiment, which is generally denoted private key EAV, experiment A and pi, where pi is the pi is my encryption scheme generator, encryption, decryption. Okay. And the steps which I have described above are more systematically given as this: the adversary A outputs a pair of messages M0, M1 belonging to M. Second, a key K, K is generated using gen, and uniform bit, and a uniform bit which is either 0 or 1 is chosen. Then the ciphertext is computed. Ciphertext C, which is an encryption under K of MB, is computed and given to A. And given to A. So C is often referred to as the challenge ciphertext. Okay. 3. A outputs a bit B prime. And 4. The output of the experiment is 1 if B prime is equal to B, i.e. They have A has guessed the message correctly if it is M0 or M1, and 0 otherwise. Okay. We write priv K EAV A comma pi is equal to 1 if experiment succeeded, if output of experiment is 1. Okay, and we in that case say that A succeeded. Okay, so what is the definition that we are using? what is the alternate definition of perfect security? Perfectly secret encryption definition. Encryption system pi. Encryption system pi, which is equal to generator encryption decryption with message space m is perfectly indistinguishable, is perfectly indistinguishable if for every a it holds that the probability that the experiment succeeds, which is prove a pi EAV is equal to 1 half. Okay, so if for every a the probability is 1/2, then we say that the system is perfectly indistinguishable. Okay, note the system is not perfectly indistinguishable even if the probability is less than 1/2. Okay, because that would mean that if the probability is less than 1/2, I can design some algorithm which fails for it more than half the time. Which means if I design an algorithm which outputs the bit exactly opposite of my previous algorithm, it would succeed more than half the time. Okay, so that's why it is indistinguishable only if it is exactly 1/2, not more nor less. Okay, and then lemma 2.6 encryption scheme pi is perfectly secret if and only if it is perfectly indistinguishable. It is perfectly in this the STUDINGUISHBL, perfectly indistinguishable. That's a long word. Okay, proof. One way is much easier than the other. Okay, so I am not going to prove that if it is perfectly secret, it is perfectly indistinguishable. Homework. Okay, I will give you a hint. Use lemma 2.4. Lemma 2.4 definition of perfectly secret. Definition of perfectly secret. Divide it into two cases. Divide into two cases when experiment succeeds and when experiment doesn't. Okay, or when b is equal to 0 and b is equal to 1. Okay, that's my hint. It's much simpler than the other direction. In fact, it's pretty straightforward once you have it. Okay, you just have to actually compute it by cases, and it's pretty easy. The other way is slightly more annoying. Okay, we are again going to use lemma 2.4 definition of perfectly secret. So assume not perfectly secret, perfectly secret. Therefore, there exists messages m1, m2, m1 comma m0 comma m1, m0 comma m1 belonging to m, and a ciphertext c belonging to c, such that, well, probability that the ciphertext that encryption under k of m0 is equal to c is not equal to, actually, let me call this c1, maybe c1. Okay, is not equal to the probability that the encryption of m1 is equal to c1. Okay, so assume there are two such messages. Then let A be an adversary which outputs, let A be the adversary, be adversary which outputs m0 and m1 in step 1. Okay, and here's what A does. A has to guess whatever the ciphertext is going to get. Then if A receives ciphertext, if A C EIVE, yes, EI receives any ciphertext C prime not equal, actually just C not equal to C1. Okay, then A decides randomly. So then A outputs random bit, then A outputs random bit B prime. Otherwise, if it gets B, otherwise, if C is equal to C1, then A outputs 0. Okay, B prime is equal to 0. B prime is equal to 0. So if my ciphertext is C1, it outputs 0 always. If the ciphertext is not C1, then it just chooses a bit randomly. Okay. Now, because the probability that the message M0 and M1 is chosen is half, we have that the probability that the experiment. Okay, I'm not going to write the entire thing. Priv, EAV, AK, A pi, everything is 1. So I'm just going to say priv A pi is equal to 1 is equal to 1/2 probability, 1/2 times the probability that the experiment is 1 A pi is equal to 1 up to the constraint that the message was M0, right? Technically, this would be times probability of message being M0, but that is exactly half, so that is already written, plus 1/2 probability that the encryption, the experiment succeeded and the message was actually M1. Okay, now let us compute the probabilities of each of these. Probability that the message, that the experiment succeeded and the message was M0 can be divided into cases again, where this means either either the encryption was C1 or the encryption wasn't C1. This is probability that the experiment succeeded, a comma pi is equal to 1, and so this symbol is and, the encryption was C1, encryption by K M0, right? Or plus probability that the encryption was 1 and the message was not equal to C1, M0. Right. Well, let's see. In the first case, if the encryption was C1, then the message is always going to succeed, right? Because I am always outputting that, as soon as the encryption is C1, I'm always outputting 0. So this case always succeeds, right? As long as encryption is C1, the condition that probability the experiment succeeded is redundant. So this is same as probably C1 is equal to encryption K of M0. Okay? Plus, what happens in the second case? Well, in the second case, I am outputting a random choice. If my ciphertext is not C1, I am choosing a bit randomly. B prime is equal to either 0 or 1. So I'm going to succeed with probability 1/2, right? So the extra condition that the experiment succeeds happens with 1/2 probability. So this becomes times 1/2 times probability that C1 was not equal to encryption M0. Okay, great. So this is my probability. Oops. This is my probability for the experiment succeeding if my original message was M0. Okay. Now let us do the same for probability of and probability that the experiment succeeds if message was 1 and M is equal to M0. Now keep in mind this is going to be exactly the same sum as this. Okay, there are going to be same cases, right? But something important happens. In this case, we said that this case is redundant. as as if C1 was the encryption, we are always going to guess M0, and the experiment will always succeed, right? My bad. This should be an M1, not M0 here. M1, right? We said that this will always succeed. So let me just actually just say that prev a prime is equal to 1 and C1 is equal to encryption M1 plus probability that priv a pi is equal to 1 and C1 is not equal to encryption K M1. Now, we are never guessing if the encryption is C1 and ciphertext is C1, we are never going to guess that the bit is 1. We are always going to guess 0. So the probability of the first case is now, in fact, 0. So let me erase this one, actually. Is equal to 0. And for same reason as before for the other one, the probability if the encryption is not equal to C1, then I'm just guessing randomly which bit is going to be. So it's going to be half, right? So I get that this is equal to 1/2 times probability that C1 is not equal to encryption K M1. Okay, and therefore, the total probability of my experiment succeeding, which was probability that private a pi is equal to 1, which is the sum of these two cases, is actually equal to 1/2 times, well, either my experiment is, either the message chosen is M0 or the message chosen is M1. Each of them happens with half probability. So I'm using this sum right here, right? 1/2 probability if the message was M0, we have said this is probability C1 is equal to encryption K of M0 plus 1/2 times probability C1 was not equal to encryption K of M0 plus 1/2 times 1/2 probability that C1 is not equal to encryption K of M1. Okay, great. Now, the probability that the encryption was not equal to C1 is what? It is 1 minus the probability that the encryption was C1, right? There are two possibilities. Either it is C1 or it is not C1. So I get this is 1/2 probability C1 is equal to encryption K of M0 plus 1/2 times 1 minus the probability that the encryption was actually C1, right? Oops. plus 1/4, or yeah, plus 1/4 probability that the encryption was not equal to M1. Okay, simplifying things out, 1/2. If I open this I get 1 minus 1/2, so I get 1/2 probability encryption is M0 plus 1/2, so I get 1/4 plus 1/4 probability C1 is equal to encryption of M0 plus 1/4 probability C1 is not encryption K of M1. And now we use the fact that this is not equal to the probability that C1 is equal to encryption of M1. Okay, the starting assumption on the way my M0 and M1 were chosen was that these two probabilities are not equal, that C1 is the encryption of M0 and C1 is the encryption of M1 are not equal. Okay, encryption K of M1. Well, either the encryption is M1, C1 is the encryption of M1, or C1. If you're encrypting M1, either you get C1 or you don't get C1. These are the only two possible cases. Together, they give you 1. So 1/4 plus 1/4 is equal to 1/2. And therefore, since there is a not equal to there, I get the probability of my experiment succeeding, A pi is equal to 1, is not equal to 1/2. Right? And therefore, the system is not perfectly indistinguishable. Therefore, not perfectly indistinguishable. Indistinguishable, which is what I wanted to show, right? Because I started with something not perfectly secure, and I have shown that it is not perfectly indistinguishable. So combined with part the other direction which I have not proved, we have together shown that this system, that perfectly indistinguishable implies perfectly secure. Okay, let us do an example. We will show that the Figner cipher is not perfectly indistinguishable. The Figner cipher is not perfectly indistinguishable and hence not perfectly secure. Okay, so here's my setting. Let pi is equal to Figner cipher for 2 character strings. Figner cipher for 2 character strings. Okay, and period is chosen uniformly between 1 and 2, and period chosen uniformly in 1, 2. Okay. We want to show an adversary. We'll show adversary A such that probability of priv A pi is equal to 1 is greater than 1/2. Okay? Here's my adversary. Adversary A does the following. Does first output M0 is equal to AA, M1 is equal to AB. Okay? And second, upon receiving the cipher challenge text, upon CEIVI, the ciphertext, challenge ciphertext, it outputs, well, C is equal to C1, C2. Do the following. Do following. If C1 is equal to C2, output 0, else 1. Okay, so if it says that C1 is equal to C2, it should output 0, otherwise it should output 1. Okay, the computation is very similar to the proof, but it's going to be slightly annoying, but it's very similar to what we did. Okay, so probability of the experiment succeeding, A pi is equal to 1, is probability that 1/2 times probability that the message chosen private A pi is equal to 1, and message chosen was, well, B0 is equal to 0 plus probability that priv A pi is equal to 1, B is equal to 1. Okay, so which is equal to, well, 1/2. What does it mean? How am I succeeding? 1/2 probability. In the first case, if my experiment is succeeded and B0 is equal to 0, that means A outputs 0 and B is equal to 0 plus 1/2 probability A outputs 1, B is equal to 1. Okay, where B was the uniform bit chosen if my message is going to be M0 or M1. Okay, so B is equal to 0, B is equal to 1 is basically saying M0 is M is equal to M0, M is equal to M1. Okay, so let us calculate the probability of each of these. The probability that A outputs 0, B is equal to 0 is what? Well, A outputs 0 only if A is equal to AA, right? If the condition is going to be AA. So in the first case, if period is 1, then it happens always, right? When you're dealing with period 1, that's basically the shift cipher, whatever you're shifting by, it's always going to, so let me say half probability half times if the period is one, you're always going to succeed, right? And the probability of the period being 1 is 1/2. So 1/2 times 1 plus 1/2 times, well, now the period is 2, right? If you have two different letters chosen, so if your two different letters were chosen, then you're not going to get AB, A. C1 is equal to C2. Sorry. From the message A, you're not going to get C1 is equal to C2 if two different letters were chosen in your period. Sorry, in your key, right? So this is equal to 0.52. Okay, let me just write down explanation. When B is equal to 0, C1 is equal to C2, right? And C1 is equal to C2. Either key is equal to key is period 1, has period 1, or both characters of the key are same, or period 2 and both characters are the same. Okay. If the key has period 1, doesn't matter what the key is, whatever happens, you're succeeding. If the period is 2, the probability that both characters are the same is 1/26. The character of it doesn't matter what's the first one you choose, the second one has to be the same. There are 26 choices, so it's 1/26. Okay. Probability that A outputs 1 and B is equal to 1 is what? When B is equal to 1, when B is equal to 1 and C1 is equal to C2, sorry. What was I saying? Okay, right. And C1 not equal to C2, right? So when B is equal to 1 and C1 is not equal to C2, the only way that can happen is, can it happen if the key has period 1? Can't. If the key has period 1, then C1 is definitely not equal to C2, right? So either key. Okay, so instead of calculating the probability of when it happens, let us calculate the probability of what is the only time it does not happen. Okay, so is equal to when b1 is equal to 1 is equal to 1 minus probability b is equal to 1 and c1 is equal to c2. Right, these are the only two cases. And when does this happen? Equal to when the period is 2, the period is 2, and the first character is 1 more than the second character, and first character is 1 more than second character, which happens in 1 over 26 cases. Which happens in 1 over 26 cases. The probability that the period is 2 happens in half the cases. So this is 1 minus 1/2 times 1 over 26. Okay. This computation is in the book. I apologize if I'm stumbling and it's unclear. Okay. Yeah. And this is approximately equal to 0.98. Okay. Then the probability of my experiment succeeding, a pi is equal to 1, which is the sum of these two probabilities, is 1/2 times 1/2 plus 1/2 times 1 over 26 plus 1/2 times plus 1/2 times 1 minus 1/2 times 1 over 26, which is equal to about 0.75, which is greater than 1/2. Okay, and this means that the Wigner cipher for two character sequences is not perfectly indistinguishable. Okay, that is about perfectly indistinguishability. Okay, so let us end this section with this chapter with Shannon's theorem. Shannon's theorem. So what is Shannon's theorem? Well, Shannon in about 1930s-ish gave a characterization of what it means to be perfectly secret. He was the first one to talk about what it means by perfectly secret and how things should be and everything. And while the theorem in itself is also interesting, it also gives a very strong condition on what it means, when is the only time something is perfectly secret. Okay, so some note: the theorem assumes that the message space is equal to the size of the message space should be equal to the size of key space should be equal to the size of the ciphertext space. Okay, now we have already mentioned that for perfect secrecy, we should have that secrecy that K should be greater than or equal to M, right? If the key space is less than m, we have shown that there have to be two different messages who cannot be encrypted to the same ciphertext, right? Now, it is easy to say that correct decryption requires that the ciphertext space should be bigger than the message space, right? Otherwise, if you take two messages and encrypt them, two of them are going to the same ciphertext, right? And then you would not be able to decrypt that ciphertext, right? And therefore, in a way, um, in a way, the message space being equal to the key space being equal to the ciphertext space is optimal. Okay. So we have talked about one-time pad having this problem that the key space was too big and it has to be equal to the message space. And Shannon's theorem is going to be emphasizing that for perfect secrecy, you cannot do away with that. It is something that you have to have. So theorem 2.11, Shannon's theorem. Let generator, encryption, and decryption, generation, encryption, and decryption be an encryption scheme. With message space m for which with message space m for which m is equal to k is equal to c. Okay, then the scheme is perfectly secret. The scheme is perfectly secret if and only if the following holds. First, every key chosen, every key k belonging to my message key space k is chosen with equal probability, equal probability k to the negative 1 by the generating algorithm, gen. And second, for every message m, in m, and every c in c, there is a unique key. There exists a unique key k in my key space k such that encryption with key of m is equal to c. Okay. Proof. We'll first show that the encryption satisfies 1, 2, then it is perfectly secret. So we are first showing this way. If it satisfies 1, 2, then it is perfectly secret. The proof is the same as a perfectly pad secrecy. So we have seen this before. Okay. For arbitrary C and M, fix arbitrary C belonging to C and M belonging to M. Let K be the key, be the unique key such that encryption of M is equal to C by the key. Right? This key is guaranteed because of condition 2. Such a key exists. Then the probability that my ciphertext is C, given that the message is M, is going to be exactly the probability that the key chosen is K, which is 1 over the size of K, okay, which is K inverse, right? And therefore, so the probability that the ciphertext is equal to C is, well, summation M is in a message space M, probability that the ciphertext is equal to C, given that message was equal to M, times probability that the message is equal to M, and did I miss something? Nope. No, that's fine. Yes, is equal to, this, okay, I will just write it in full details. 1 over K times probability that the message probability that the message is equal to M. Pulling the 1 over K outside, 1 over K times summation M belongs to M, probability that M is equal to M. And, well, the message, it has to be one of these, so the summation over everything is 1 is equal to 1 over K. Right? Both of these are equal. And therefore, thus, for any distribution, this holds for any distribution. It doesn't matter. This holds for any distribution. This holds for any distribution on M, right? And therefore, we get, for any distribution, probability that M is equal to M, if you know that the ciphertext is equal to C, is equal to, well, from Bayes' theorem, probability that C is equal to C given M is equal to M, times probability that M is equal to M, all over probability that C is equal to C. Well, we have already calculated both of these to be K inverses. K inverse, sorry. K inverse probability that M is equal to M over probability, this probability also we have calculated to be 1 over K, or K inverse. Hence, this probability is equal to probability M is equal to M, and hence scheme is perfectly secret. Therefore, scheme is perfectly secret. Okay. Now, for the other way around, assume that the scheme is perfectly secret. We want to show conditions 1 and 2 hold, right? So fix some key, fix C belonging to C. So there must be some message. There must be some message. There exists M star belonging to M such that probability of M star when encoded is C is not equal to 0. Okay, this means that there is some message. Well, if it is not there, there is no such message, then C shouldn't be in the ciphertext space. That's why we have to have one of them so that this is non-zero. Okay, then by lemma 2.4, we get that probability, therefore probability ENCK of M is equal to C is not equal to 0 for every M in M, since lemma 2.4 says they have to be all equal. Okay, therefore for every M there is some key, there is some set of keys Ki. Therefore for every Mi belonging to M, there is a non-zero set Ki, which is a subset of K, such that encryption with Ki, with K of M is equal to C for every Mi is equal to C for every K belonging to Ki. Okay, now also if I is not equal to J, then Ki intersection Kj has to be empty, otherwise you have trouble, right? Otherwise you cannot have correctness due to correctness, or else correctness fails, or otherwise correctness fails. Why? Because if the intersection is non-empty, suppose there is some K, then encryption under K of M1 is equal to encryption under K of M2 is equal to C. And you had an exercise last time which said that if that happens, then M1 has to be equal to M2, right? X has to be equal to 1. Well, since we have assumed that since key space K is equal to the size of M, that means that each Ki contains exactly one key. Each Ki contains exactly one key, and this shows that each key is unique. Now lemma says, lemma 2.4 again shows for every M1 comma M2 belonging to M, we have that probability that the key K is equal to K1, Ki is equal to, well, the probability that the encryption of the message mi is equal to c is equal to probability of encryption of mi is equal to mj is equal to c. mj is equal to c, as we assumed perfect secrecy, right? And that is equal to probability that key is equal to kj, kj, and therefore this means that each key is chosen with equal probability. Therefore, each key is chosen with equal probability, fulfilling condition 1, okay, i.e. k, size of k to the negative 1, k to the negative 1, and therefore, as required by condition 1, both therefore condition 1 is fulfilled, and both condition 2 was fulfilled from here, exactly one key, unique key existing. Now we have shown condition 1. This means that both the conditions of my Shannon's theorem are satisfied, and that completes my proof. Okay, so Shannon's theorem is useful for deciding whether a given scheme is perfectly secret. Okay, it is easy to check conditions 1 and 2. Shannon's theorem gives an easy way to check for perfect secrecy. Gives an easy way to check for perfect secrecy. Perfect secrecy given message space is equal to key space is equal to the ciphertext space. Okay, but it also emphasizes how strong a condition of perfect secrecy is. Okay, it is also telling you that for perfect secrecy to hold, your system needs to be really rigorous, right? And so we would like to know, can we relax our conditions on perfect secrecy and still have things be reasonable, be usable, okay? And that is what we'll be looking at in the next chapter, okay? And starting next week. Sorry, not next week, next video. Okay, I'll stop this video